Thank you, David.
Yeah, I changed the name of the talk because I thought, why learn C? You kind of, instead of doing why learn C, I thought I'd look at, what kind of things C is used for, and then you can work out for yourself whether you want to bother learning it, or if you know it already, whether you want to have a look at it again. So because it's about C, I thought we'd start by looking at a Java program. Which, if you look at it, this is clearly a very crippled example that I've done deliberately so it'd be easy to convert it into C. Okay, so it's not very object-oriented. But you've got a class that's got a couple of attributes, and then a main method that goes and creates an instance of the object, sets some attribute values, and then calls a function to display the contents. So that's like the Java program. And I think the kind of closest thing you can get to working in a similar way in C is something like this, which looks a lot longer and a lot more horrible. And the reason is that what happens when you do things with like local variables and object references in Java, that V object reference will sit on the part of the memory called the stack, and then the object that gets created on the heap. And the heap is like the Wild West of memory, where stuff gets created there, and generally in a language like C you have to go and manage it yourself. But because Java's got a garbage collector that takes charge of the heap when stuff gets out of reference, then it can clean it up again. So to do the same kind of thing with stack and heap variables, this is what you do in C. So you haven't really got object references. Closest thing you're going to get is a pointer. So it creates a pointer. Malloc is a function that creates an area of memory on a heap, and you have to say how much memory you want, kind of in bytes. And then you have to do some kind of weird casting thing to make the syntax work. And then instead of saying v dot, because v is now a pointer, you have to do v hyphen greater than x. And it's kind of, because it's creating things on the heap and because C's not got garbage collection, you then have to free the memory yourself afterwards, because C's not got a garbage collector. Its famous supposed flaw. And the reason it probably hasn't got a garbage collector is because most garbage collectors are written in C. But normally in a C program, you wouldn't write it that way. You'd write it in a slightly different way, which actually looks much closer to the Java version. But underneath the surface, it's actually working in a very different way. Because what you can do in C is you can actually, in Java, you can only really you can put primitives on the stack and you can put object references on the stack with little 32-bit pointers. But in C, you can actually put an entire, in this case it's a struct, it's not really an object, you can put larger data structures directly on the stack. And the great thing about the stack, it's got its own garbage collector built in, because you put things on the stack and then you move the stack pointer back and you can just ignore whatever rubbish you put on there. So for a C program like this, you don't actually need to allocate memory dynamically and free it. It just happens implicitly because it's all being done in a kind of stack-based way. So that was one of the things that they actually got rid of when they went from C++ to Java. They kind of simplified it and they said, well, stack processing, programs could be quite fiddly to work out how to do it, to not have side effects and stuff on the heap. So they gave this much simpler way of working where data got allocated space on the heap and then the garbage collector tidied it up. But it does allow you to actually work in a kind of much more stack-based way. Now, one of the good things about that is if you're going to write, I don't know, a language like Haskell. I don't know much about Haskell, but I know that Haskell actually can convert itself to a C program. And I suspect one of the reasons that they actually output C programs is because they can do this kind of tuning with the stack because it's much more efficient. The other thing is that it means if you're writing a C program, you can write it in a way that you can either manage your own garbage collection, or you don't need garbage collection at all if you're working in a kind of stack-based way. So it can be quite efficient, so you can actually do things which are quite low-powered. So that's a kind of an obscure technical point, but what's the kind of implication? Why would you actually want to use a C program rather than anything else? And I think if you look at the ways that C is currently used, it's normally used because you want to have more control over the performance of a thing. And performance doesn't necessarily just mean being quicker, it might mean being more efficient in power terms. Or it's something where you just need a very small program that's going to be quite simple. Now if I show you an example, if I can find it. I don't know if anyone's used an Arduino. It's an Arduino, it's a programmable microcontroller. It's a very sort of low-powered computer system. And most Arduino programming is done in C. And the reason it's done in C is because a microcontroller just takes inputs from sort of digital signals and gives you a number from 0 to 255, and then it does outputs to things that go from 0 to 255. And most Arduino programs are just a big loop, which is why they generally have a function in them called loop. And this is an example program my wife wrote that it just reads values from a couple of inputs and it works out if a circuit's being closed. And if the circuit's being closed, it comes down here and it prints out some text onto a serial port. And if the circuit's been left open, it prints out another piece of text on the serial port. Now I think I might have a video of this program working, if I can remember the URL. So this is actually like a plant feeding program. So what it's doing, I'll pause it before it starts. Okay. That is supposedly a plant pot. It's actually a little cup with some tea bags in it that have been dampened with 2 galvanised nails, and then it's got some leads that can be connected. And the idea is that you can actually stick the galvanised nails inside a plant pot. And when the thing becomes dry, you get no circuit between the 2 nails. And so you get very low value on the input port, and then it says, feed me on the serial output. And then as soon as you touch those nails together, it's as if the soil's got damp, and then the water connects the 2. And the serial port's actually been plugged out through a USB adapter, and it's going into a computer that's just being used as a kind of big speech synthesizer.
App feed me, 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 feed me. Thank you, Seymour. Feed me, feed me, feed me.
I mean, in a case like this with the Arduino, you've got sort of both factors. You've got code that's not going to get terribly complex, because C code, you can write really big programs with C code, but the problem is it gets unwieldy really quickly. It's not object oriented. You know, that's why C++ was invented, so you can expand it in a certain way. So you've got programs that are very short, but you've also got kind of performance issues that you want to solve. Now, performance, Java's no longer slower than C. You know, it used to be that the Java programs were always the much more sluggish ones, but if you're running lots of programs together on a platform, the Java ones are probably going to be quicker, because Java programs are all sharing a JVM. They can coordinate the garbage collection, they can work in a much more efficient way. But in a situation like a small device, your performance issues then, you start to think about being able to run the processor at a slower rate, and having kind of smaller startup times and those things. So for smaller devices, C starts to make a lot more sense, particularly if it's going to be doing something very simple where it's just going around in a loop and applying a little bit of logic. I've actually got, that's like a basic Arduino that you normally get. There's also one I want to pass around called a LilyPad Arduino, which is a sort of an equivalent circuit. It's really tiny, but it's actually, that one is washable and you can kind of build it into fabrics and things. And I believe that Arduinos are becoming like the standard way of creating devices to plug into Android phones. So, you know, if you're going to do those things, I saw one this morning, it was actually used as a kind of stress meter built into a watch. So those kind of small devices, C makes a lot of sense. You could probably get Java in there, but not really to a lot of advantage. You'd have a lot more memory overhead, it would take more time to start up, and the language wouldn't actually be necessarily easier to program for those kind of small programs. So that's the kind of the first category, where you've got very small devices, very simple logic, and you want to make them low powered, and you want to get them to start up quickly. A second kind of case where you might want to use C, I think, is if you're going to be doing a single kind of task repeatedly and you want to do it very quickly. So if you've got some kind of library, you know, you get lots of libraries that you're building on the like Linux distros. In those kinds of cases, they're likely to be fairly quick and efficient, because C libraries will load very quickly, you'll bind to them very quickly, and if they're just doing the same thing over and over again, inside the library it's probably not doing an awful lot of very complex processing. So it makes sense to actually, for certain specialised cases, to just use C to write the library, because that's going to be the really slow bits, and then you can bind to it with another language like Java or Python. Now for this example, this is actually a program that's using a library called OpenCV. I don't know if anyone knows OpenCV. You know OpenCV. What's your PhD in? OpenCV is a computer vision library. And you can use it a bit like a regular expression engine for images. So you can say, here's an image, and you can give it what's like the equivalent of a an image regular expression. So like an image a normal regular expression is like a long piece of text that no one understands, that you finally work out how to do, and then you give it to a piece of code and it can find patterns within text. And in OpenCV you can use a thing called a Haar cascade. And a Haar cascade is a really, really huge XML file that will put in a pattern for a particular part of the image it's looking for. So if I actually switch to terminal, just have a look. So ls. So I've got this program called detect.c. If I make detect, and then if I run it, now what this is going to do, it's actually going to switch on. It's switching on my webcam, and it's designed to look for elements in a human face. What do I do? I'll switch this into the foreground. The closest thing I've got to a human face is mine. So if I put it in there, which I think is quite cool, as it kind of follows me around. Now, if you use Facebook, it's actually impressive. It will do it even with my glasses on, I've noticed. And occasionally, if I do this with my mouth, no, I can't quite get it. Occasionally, get bits of your face to kind of, I'll leave it there blinking. Actually, no, like my. Oh, excellent. Okay. So, if you ever use sort of Facebook, and I don't know if they've switched it off recently, where you go along and it will find people's faces in the image. So I think that's using OpenCV behind the scenes. And if you use StreetMap, and StreetMap kind of blurs people's faces. I even saw, like, there was one for Nottingham where they got the back of a bus and it got an image. It was like a drawing of Elvis, and they blurred Elvis's face. So they're actually using, something like this to do the same thing. So if I show you what the code looks like for that, it's actually not that long. So it's got two functions in it. It's got main, which in C is just like main in Java. And the first thing it does, it goes and creates some bits of memory, because you always have to do that in C. And then this thing here, cascade peepers, that's the thing that's going to load up this gigantic XML file. I actually put it check, so it was loaded, that was a professional thing. And then basically it says if I manage to load this thing, then it just does like an endless loop that goes through. This line here, CV query frame, that just opens up the webcam and captures a frame from the webcam. Frame copy, to make life easier for OpenCV, because it's kind of really good at grayscale images, it's a bit crap at colour images. So what frame copy is going to be is like a grayscale version of the image. There's a bit of kind of rotatey things, because different webcams actually give you images in like portrait or landscape, so it works out how to rotate that. And then finally it calls this function called detect and draw. And detect and draw is the other function. And that's over here. So detect and draw, that basically just takes the captured grayscale image, and then in here, this is the thing that's like a regular expression. So it says, analyze my image, and then using this cascade peepers, which is again, like this sort of huge XML file, try and find all of the eyes in the image. And then in here I say, if you can just find two, because occasionally it will find like 15 things around the screen that look a bit eye-ish. If it only finds two, it goes and finds the rectangles of where they are. And then finally this bit down here is the thing that says over the top of the image, I've got some little heuristics in there that look to make sure my eyes are not too far apart or anything. And then it's got a little randomizer that 1 in 10 times it will decide to draw it like I'm blinking, and then otherwise just draw the eyes. And then finally has to release everything afterwards. Okay. Any questions on that?
Can you load up the IXML file?
Oh yeah, absolutely. I think I might have it on detect C. I will. Hang on. It is text, and it is enormous.
That's the whole thing about why it works. That somebody
508K.
Somebody trained this classifier. Because I understand it's.
Yeah, and you actually, when you get the OpenCV library, you get about 30 things that will do things like, find that bit of your face, or just a left eye, or just a right eye, or an ear, or a nose. And it's quite useful, when you're getting all of these sort of biometrics things where they're trying to recognise people's faces, because you can look at like the relative distances between the middle of their eyes and the end of the nose and where the mouth ends, that kind of thing. So yeah, that's it. So this is 500 and something K of really, even for XML, quite boring XML. So all of these things, but clearly no one's ever typed these in. They must have just analysed thousands of faces to actually work out what an eye looks like. Right, what I'll do then, so for the final one, OpenGL, anyone in this room who's not Richard that's done OpenGL? You have, excellent.
Yeah.
Well, you know in OpenGL, you basically, OpenGL, it's an interface for graphics cards, and graphics cards are only really good at two things. One thing they're good at is dividing numbers very quickly, so they can do perspective calculations. And the other thing they're very good at is drawing triangles. So they can't draw squares, but they can draw triangles. So with a graphics card, you normally create like a 3D model, and you send it down the graphics pipeline, it goes onto the card, and that says where all the bits are in your 3D space. But then it needs to actually draw them on the screen. And to draw them on the screen, it normally uses these things called shaders. Well, it always uses these things called shaders. And shaders are written in shader language. And shader language is just C. So if I show you, this is WebGL. So this is just doing OpenGL inside a web page. And you've got two types of shaders that you can use with OpenGL. You've got vertex shaders. And vertex shaders are pieces of code where if you've got a point in 3D space, it needs to work out where it's going to be on the screen in 2D space. So they're the ones that basically do the perspective calculation. Now the perspective calculation in this vertex shader here, so that's a vertex shader, actually takes place on that line there. And what it's doing, it's just taking V position, which is position in 3D space, it's multiplying it by a matrix, and it's creating the GL position, which is effectively a place on the screen. Okay. So again, it's got these two elements of you've got a relatively small amount of code, albeit a small amount of code that's doing some very complex mathematics, but the difficulty is in the maths, it's not in the code. And it's also a piece of code that's going to be run a huge number of times. Whenever it needs to know anything from 3D to 2D, it's going to need to run this vertex shader. So you could be talking about potentially sort of doing millions of these a second. So you're not going to write something like that in Java because it's just going to be, what would be the point? It's a small piece of code. If you were going to do it in Java, it would probably actually get longer because you'd have to turn it into a class and things. So we've got the vertex shader that calculates 2D position from 3D. And then you've got what's technically called a fragment shader, but what everyone calls a pixel shader, which is this bit here, which I've got an even shorter example. That's just some gubbins to make WebGL work properly on my machine. And what this does, this says, well, okay, I know where a pixel's going to be on the screen. Now I need to know what colour it's going to be. And in this case, so the output is this GL frag colour variable. What I'm doing, I'm setting it to a colour, so that's basically going to be green. All the values go from 0 to 1, red, green and blue. And I'm giving it an alpha value of 1, so it's going to be kind of opaque. And so I'm saying that every time it needs to decide the colour of something in an image, it's going to basically make it bright green. Okay, so we've got the big lump of mathematical stuff at the top that does the calculation from 3D to 2D. And then there's that second, the pixel shader, the fragment shader, that works out what the colour of things is. So if I go and open up the web page, I'd be amazed if this works with the video in the background. So what I've got is just like a series of spheres. But at the moment they kind of look like it's just drawing circles on the screen because everything is a very flat kind of green colour. What we can do with that, if I switch to example 2, down here, up in this is going to kind of go into mathematics, so feel free to throw things at me. What we're doing up in the fragment shader, it's working out it's giving it a light direction. So you've got light coming in from a particular angle. And when it's created a sphere, which is just made up of dozens of little tiny triangles, each of those triangles, it knows like a surface normal. It knows which way's out. And if you're doing a lighting calculation, if you know which direction the normal is of a surface, and you know what angle the light's coming in, it's you do the dot product between the two, and that gives you like the brightness of light falling on that point. So that's what V dot is. It's basically a value from 0 to 1. That's the brightness of that surface given a light direction. What it's doing therefore down in the pixel shader is just instead of just doing green, it's then multiplying it by the brightness. So if I switch back to the browser, this thing does tend to crash my computer, so I'll apologise in advance if it freezes up for the next 20 minutes, but at least it'll expand the talk to an hour.
Yes.
Okay, so there we go. So it's starting to look a little bit more 3D now. So if I go through, And you'll actually see as well that if you look, because all of these spheres are actually rotating, so if you look really carefully, you can see that they're not perfectly smooth spheres, they're just kind of approximated as little triangles. Now that's probably doing, I don't know, it must be close to kind of, it's about 1,000 and something by 900 and something, so we're probably doing about 1 million pixels. And it's calculating, it's doing this kind of mathematical calculation for each one, location on the screen as well as working out what the colour is. And it's probably doing about 60, 70 frames a second. So that's 60 or 70 million times a second it's calling that code. And it's because it's not doing it in the browser. It's taking in the browser, find it, it's taking these lumps of C code, extracts them as a string in the JavaScript, and then basically passes it off to WebGL. And what WebGL will do is hand it over to the OpenGL drivers. They'll run a little C compiler that will compress it down into something that the graphics card will understand. Then send it down the graphics pipeline, it will live on the GPU, and that's where it's going to run. So it's basically running the other end of the pipeline, which is how it can run so fast. And again, you know, the GPU is not going to want anything very heavyweight like Java. So if you're going to do any kind of optimized stuff, it makes sense to do it in C. So the final version, what we're going to use now is actually use a sampler. So a sampler can take an image file, and it uses texture coordinates. So you've got a position that's on this 3D object, and then you can wrap an image around it, and it knows the coordinate of where you are on the object, and it knows also the texture coordinate, which is where you are on this image that's being wrapped around. And then the lines we've got here is that text coordinate is basically calculating where we are in some flat image file. And then it's saying, well, okay, given my current position, because I know how the surface I'm currently drawing relates to the texture, this colour value here then is going to be like a pixel that's off that underlying image that we're being displayed. And so instead of just displaying 0, 1, 0 to get green that we then light, we're actually taking a pixel from some other image file. Which, if I go and close this one, this will actually push it a bit more. Which gets to the kind of final textured version, which is quite nice given that's been done in the browser. But again, something like that you could never realistically, you can do it in Java, you can do OpenGL in Java, but the way that you do OpenGL in Java is by basically doing the business logic around the end. Like this is doing animation between things. The animation is really nothing to do with the graphics card, but you know, this animation has just been done with JavaScript. But the kind of the sharp end of the chisel is actually all being done on the card. And for those kind of very optimized bits of hardware, you're going to use C. So, you know, in general, you're likely to use C if it's going to be something where performance is going to be really critical. That's either because it's going to be doing something incredibly difficult like this, that it needs to do millions of times a second, or because it's going to be running on some tiny little device where you want to slow the chip down and you want to not use much power. Those kind of performance things is where C starts to make sense. And also typically where the code's not hugely complex, because C is much more prone to bugs. It's actually quite difficult to write really large programs. You know, you're going to be able to write operating systems in it because you have to use a language like C for an operating system. Performance is so important, you've got no real choice. But for really large scale systems, people are typically, you know, you're going to use Java, because performance on a large system, you're not going to notice the difference. So it's primarily where performance is important and where the code's not too complex. Those are the circumstances where you probably want to use C.